is on the Doppler effect. I know you guys have done the Doppler effect before, but we're gonna just discuss it in a little bit more detail, and we're going to discuss in a little bit more detail and just try and understand the concept. The concept is the most important thing. You can go over the Doppler effect multiple times, and so you can commit it to memory. But when we talk about the Doppler effect, a good example, the one given by Christian Doppler. This is the physicist who first described the Doppler effect and the mathematics related to the Doppler effect. So if you're at a train station, so that's what you use, a train station. If you're at a train station and you're standing you're stationary, you're not moving. And if the train is coming towards you and the horn of the train is going, when the train is approaching you, you hear the horn at a high intensity. And then when the train passes you, the intensity gradually decreases. So there are a number of things that's operational here. Is that you have an observer, which is you, standing at the train station. Then you have the train, which is coming towards you. Okay, and then the horn. So you have the train, which is moving, the horn, which is in the train, and it's moving with the train. And then the horn is making a sound. Okay, so when the horn is making a sound, it's sound wave. Okay, so that sound wave that the horn is producing gonna have a frequency and a wavelength, and because it's the sound in here is gonna have a certain speed. But the thing that you have to understand is that you have a moving source of sound, which is the train with a horn in it. Okay, so the moving source of sound, the train which is moving towards you, the sound from the horn, so it's coming towards you. The frequency that the sound is being produced from the horn, from the train horn, is fixed. The frequency that, this frequency that's coming from the horn is fixed frequency. It's not changing. So when you have a moving source of sound and it's coming towards you, the perceived frequency is going to be higher. Okay? Once it moves away and it's moving away from you, the perceived frequency is going to be lower. Okay? So you have a moving source of sound. Okay? So the train is coming towards you or moving away from you. That's the moving source of sound. And the horn on the train, that is the sound. Okay? The frequency, the transmitted frequency that the horn is producing is a fixed number. It's not changing. It is the perceived frequency, what the observer is hearing. That is what's changing, and it's going to change depending on whether the moving source of sound is moving towards you or moving away from you. If it's moving towards you, the perceived frequency is going to be higher. If it's moving away, the perceived frequency is going to be lower. So how does that relate to what we're doing in ultrasound? Simple. When you're doing ultrasound, you use your transducer. Transducer is on the patient's chest. You're sending out sound waves, and that sound wave is going to encounter moving blood or moving tissues, whatever you know. And if that moving blood is moving towards the transducer, which is like the observer, the perceived frequency is going to be higher. If it's moving away, the perceived frequency is going to be lower. Okay? And as we have shown you guys, the Doppler formula, which is very important, the Doppler formula tells you about the perceived frequency and hence, the velocity. The cosine, if you remember the formula, the cosine, we have a cosine theta, which is the angle between the ultrasound beam and the moving structure. To get maximum velocity, you have to be parallel. That is, the angle theta should be close to 0 or 0. The reason for that is because cosine 0 is 1. And then cosine 90 is 0. Because cosine theta is in the numerator, is on the top of the formula. So if the angle is 0, which means parallel, ultrasound beam is parallel to the flow, then cosine of 0 is 1. So you're going to get maximum Doppler shift or maximum velocity. If it's perpendicular, then cosine of 90 is 0. And you're going to get no velocity, no Doppler shift. So that's the concept. That's basic Doppler effect in a nutshell. So when the source of waves is moving with respect to an observer, okay, the observer is not moving. The transducer is not moving. It is the ultrasound, which is, of course, ultrasound travels, and then either tissue or blood, which is moving. Just like the observer at the train station. If the observer is not moving and the train is moving, okay? So you get an apparent upward shift in frequency for observer towards whom the source is approaching. So if the blood is moving towards the transducer, you get an upward shift in frequency, or the frequency appears, or it appears to increase. And when it's moving away from you, you get a downward shift. So there is no actual change in the frequency from the source, as I've said before. Okay, the frequency from the source is not. So this is another example. So if this is the observer right here, okay, let's highlight the observer. So if this is the observer, if the observer is right here, and this is the moving source of sound, which is, say, an ambulance which bleeping its horn, coming towards the observer, you're going to get a so-called upward shift in the frequency. So the frequency, it's going to appear to increase. So what's actually happening, because the speed of sound going to remain the same. So if you get an increase in the frequency, the wavelength have to decrease, because the speed of sound in any medium is a fixed number. And remember what we said, the speed is equal to the wavelength times the frequency. Speed is equal to wavelength times the frequency. So if you get an apparent increase, or you hear an increase in frequency, the wavelength have to decrease. So this is what is drawn here. The wavelength is decreasing, coming towards this observer. So there's an apparent decrease in the wavelength. The frequency increase, but the product of wavelength times frequency is going to be the same. The speed of sound in a medium is the same. It's not going to change. And then for this observer, this source of sound is moving away from this observer. So there's an apparent decrease in the frequency. So in order to make the speed of sound the same, the wavelength have to increase. Okay? Okay, so speed is equal to wavelength times frequency. So The speed of sound in any medium is fixed. So if you have an increase in the wavelength, the frequency is going to decrease because that product has to remain the same. So that's essentially the Doppler. Okay, so you need to go over it multiple times and draw it. Okay, so and then this is the same thing, moving source of sound, observer coming to, if it's coming towards you, there's an apparent increase in the frequency, so the wavelength have to decrease. So from here to there, from there to there, that's the wavelength. So wavelength decrease. And if you have an observer here, once it's moving away, then the apparent the Doppler shift or the perceived frequency is going to decrease, so the wavelength increase. So that's what's depicted there. All right. So that's all we're going to say about Doppler, but go over the Doppler formula. Okay. You have cosine in the numerator. Okay. Okay. So you try to get the ultrasound beam as parallel to the moving structure because you want to get that angle theta close to 0 as possible, because cosine of 0 is 1, cosine of 90 is 0. All right. So we're going to move on to something called traveling waves and standing waves. And the reason for discussing this is to understand when we talk about harmonic imaging, what are we talking about? When we do ultrasound today, we use harmonic imaging, use the second harmonic, and you must have seen that. So we use harmonic imaging as opposed to fundamental imaging. 20 years ago, we used to use fundamental imaging. Now we're using harmonic imaging, so the image look brighter. The only problem with that is that structures look thicker. Okay, so we use harmonic imaging. So knowing the difference between traveling wave and standing wave will give you a better understanding of harmonics. So when we talk about a traveling wave, it's a wave that is moving. Okay, so sound wave, water wave, those are traveling waves. And traveling waves are, if we talk about a mechanical wave, we already discussed mechanical wave. Mechanical wave different from electromagnetic wave in that electromagnetic wave can travel through a vacuum, and mechanical wave needs a medium in order to be transmitted. But if you create, say, sound wave by a vibrating object, if you create sound wave by a vibrating object, you get a mechanical wave, and it travels through a medium. So when I'm talking to you, it is traveling through here. So that's a traveling wave, or that's a traveling wave. And of course, waves transmit or transport energy. Okay, and the wave will continue. So the wave will continue until it encounters a boundary, or it encounters another wave. So that's a traveling wave. Sound wave is a traveling wave because it's moving from one area to another area. It's traveling through a medium, and it's transporting energy. And the amount of energy is related to the amplitude. There's a direct proportionality there. A traveling wave is not confined to a fixed space. It's going to travel until it encounters another wave or a boundary. So it is not confined to a given space. So that's a traveling, just a wave that travels, a regular wave. Regular wave is a traveling wave. So don't get lost in the the description of it. All right. So of course, when we talk about traveling wave, we talk about the wavelength from crest to crest, the distance, the time it takes from one crest to the next is the period. We talk about the amplitude, maximum displacement from rest, and it travels in a particular direction. So we went over all of this before. Um, so traveling wave is different from a standing wave. So we're going to discuss standing wave now. So you need to use your imagination and figure out what's going on. So say for instance, put we have a rope. Say for instance, we have a rope and we fix the rope to a boundary, or we fix it to the wall. So we fix the rope to the wall and we create a wave in the rope. So you're going to have that wave going towards the wall, and then when it strikes the wall, it's going to come back. It's going to be reflected. So a portion of that wave is going to be reflected, and it's going to come back to where the wave was created. So again, you have a rope, it's fixed to a wall, and you create a wave in the wall by just moving it up and down. The wave is going to travel, and when it gets to the wall, it's going to be reflected backwards. If you can create a wave in such a way that the wave that is traveling towards the wall is exactly equal and opposite to the wave that's coming back, the reflected wave, then you'll get a pattern. It's not really a wave. You'll get a pattern that make the wave look like it's standing still. So again, if you have a rope and you create a wave by just moving it up and down, and once it's hit the wall, it's going to produce another wave coming backwards. That's a reflected wave. So the one that you create is the incident wave, and then the one that's coming backwards is the reflected wave. If you produce a wave in such a way that when it's reflected backwards, it's equal and opposite. So it's equal and opposite to the one that you transmitted. You'll get a pattern that it looks like the wave is standing still, and that's what we'll call a standing wave. So these are the characteristics of a standing wave. It is confined to a given space in a medium. So unlike traveling wave, which is not confined to a given space, a standing wave is confined to a given space in a medium. It vibrates at just the right frequency. So you have to produce a specific frequency where the wave that is transmitted is going to be opposite and equal to the wave that's reflected. So it has to be vibrated at just the right frequency. The incident and the reflected wave is going to interfere and produce a sine wave pattern. So the incident wave, that's a wave that's moving towards a wall. When it's reflected, okay, it's gonna interfere with the incident wave and produce a sine wave pattern. At specific points along the medium, the wave or the pattern appear to be standing still, and that's what we call the nodes. And the definition for nodes is point of node displacement. So let me draw it. Again, when you get anything, you have to draw it. If you don't draw it, if you can't draw it, that means you don't understand. All right. So this is the wall. So this is the wall, and we use our rope to create a wave. So the wave is traveling to the wall. Okay. So when it's hit the wall, okay, you're gonna get so this is our incident wave. It's moving towards the wall. So this is the incident wave. Okay. So when it hit the wall, it's going to be reflected. Okay. It's going to be reflected, but it's going to be reflected in such a way that you're going to get your reflected wave, which is opposite. So now it's going to look like this. It's going to be opposite. So it's reflected. So that means it's okay. So this wave is moving this way, and the reflected wave is moving this way. Okay. So when these waves interfere, you get a pattern. It's going to give you a sine wave pattern that appears to be standing still. And the points where there's no displacement, because if a crest meets a trough, it cancels out each other. So you're going to get no displacement. The net result is no displacement. So that's what we call a node. So the point of no displacement, that's when crest meet trough, that's what we call a node. And then the point where you have maximum displacement, that's what we call an antinode. All right. So that's a standing wave. All right. So, all right. So basically the same thing. So you have your incident wave traveling here. Okay. And then you have your reflected wave, which is moving in. Your reflected wave, which is moving in the opposite. Well, your reflected wave is right there. Okay. Your reflect, that's a wave going backwards. So we said that the node is when you have crest meeting trough and they interfere, you have no displacement. So that's a node. And then your antinode is where crest meet crest and you get your maximum displacement. So again, okay, so the bright wave is your incident wave. And then once it's hit the wall and it's reflected, the lighter one is your reflected wave. This here is when you combine them. When they interfere, if you look there's a crest and a crest. Okay? So when you combine them, you're going to get a resultant. Okay? And this is the resultant down here. So you're going to get, when you combine your incident and your reflected wave, you're going to get no displacement. And the no displacement is because crest meet trough. And when it interfere, it cancels out each other. So this is a node. When crest meet crest or trough meet trough, then you get these antinodes. So you're going to get periods of node, antinode, node, antinode. So it looks as if this pattern looks like it's standing still. So this is what we call a standing wave. Okay? Standing wave. That is because you have your incident wave. When it's reflected and it interferes with the incident wave, you get a pattern that looks like it's standing still. Standing wave. You have to produce the wave with a specific frequency for this to occur. So it's not all wave that's going to give you a standing wave. It has to be at a specific frequency. So when the reflected wave meets the incident wave, it interferes in such a pattern to give you, when the crest meet trough, you have no displacement, so that's a node. When crest meet crest, you get antinode, or if trough meet trough, you get an antinode. So this is a standing wave pattern. Okay. Again, you have your incident wave interfering with the reflected wave to give you nodes. This is point of no displacement. Okay, if this is your resting position, right? This horizontal line is a resting position. Then point of no displacement is called a node. And it's the node because when the incident wave interfere with the reflected wave, you know, crest meet trough, you have point of no displacement. Antinode, however, is when crest meet crest or trough meet trough. These are antinodes. Okay? So standing wave is actually a wave pattern. It's not a wave. It is the interference of two or more waves. It is not a wave. It is the interference of two or more waves. So with the standing wave pattern, it's a vibrational pattern within a medium. It's a vibrational pattern within a medium. The frequency has to be just right. So you need a specific vibrational frequency of the source. It causes the reflected wave to interfere with the incident wave. Specific frequency. So that the incident wave interferes with the reflected wave to give you the standing wave pattern. The interference occurs in such a manner that specific points along the medium appear to be standing still. So it will look like it's standing still. Okay? The frequencies are known as harmonic frequency. So what I'm saying to you is the frequency that you use to produce these standing waves is called the harmonic frequency. So when you hear someone talk about harmonic frequency as opposed to fundamental frequency, it is the frequency that is going to produce these standing waves. It is the frequency that will produce the standing waves. So again, it's a standing wave is a wave pattern. It's not really a wave. It is the interference. When the incident wave interfere with the reflected wave, you get a pattern, look like it's standing still. The nodes are point of no displacement along the medium. It is destructive interference. That is when you have crest meeting trough. So it is a destructive interference between two waves traveling in opposite direction along the same medium. That is what the node is. So these points are nodes. Nodes. Okay? It is an interference. When it is a destructive interference when you have crest meeting trough. Okay? And then the antinodes are points along the medium that vibrate back and forth between points of large positive displacement and points of large negative displacement. So your antinodes are actually constructive interference. Crest meet trough, trough meet trough. So constructive interference will give you antinodes, and destructive interference is going to give you nodes. Okay? Antinodes, nodes. Standing wave pattern. The frequency that's going to give you the standing wave pattern is called the harmonic frequency. All right? Again, nodes, points along the medium that appear to be standing still, and there are points of no displacement. Your antinodes, points along the medium that undergo vibrations between a large positive and a large negative displacement. So these are constructive interference. So points of maximum displacement, constructive interference. Again, that's what it looks like. Okay, so your nodes are destructive interference, anti-node constructive interference. So again, standing wave is actually a pattern. It's not actual wave. It is the interference when two or more waves interfere. That's what gives you a standing wave pattern. So when someone talk about first harmonic, so you're going to hear them talk about first harmonic, second harmonic, third harmonic, and fourth harmonic, and so forth and so on. So when they talk about first harmonic, the standing wave just going to have one antinode. So first harmonic is depicted on top. It has one antinode and there are two nodes. Okay? Again, nodes are points of no displacement. Antinodes are points of maximum displacement, either positive or negative. So the first harmonic, you have one antinode. Second harmonic, you have two antinodes. Third harmonic, 1, 2, 3 antinodes. And the third harmonic, you have 1, 2, 3, 4 antinodes. Okay? You need to draw it and you need to go over it. Okay, standing wave pattern. So it's a frequency that produces these standing wave pattern. That's what we call harmonic frequency. The first harmonic have one antinode. Second harmonic, two antinode. Third harmonic, three antinodes. And the fourth harmonic have four antinodes. The antinodes are points of constructive interference, where crest meet crest, trough meet trough. Your nodes are points of no displacement, where you have destructive interference. Crest meet trough, or trough meet crest. Okay, so this gives you an insight when we talk about harmonic, because you're going to hear about harmonics. First harmonic, second harmonics, third harmonic, so forth, so on. Okay? All right, so again, second harmonic have two antinodes. So when you talk about the number of harmonic, it's related to the number of antinodes. And then if you add one to that, you get the number of nodes. Okay? Third harmonic gonna have three antinodes, and so forth, so on. Okay? All right. All right, so the reason why we're going through all of this is because sound is a wave, and you need to fully understand a little bit about waves. Okay, we talk about medium, could be air, water, tissue, whatever. Mechanical wave that requires a medium. Waves transport energy. We talk about electromagnetic wave. It do not require a medium. It can transmit through a vacuum. We talk about sound wave as a longitudinal wave, okay? And we can create sound wave by vibrating object. It's going to transport energy through the medium. The individual particles in the medium vibrate, okay? Sound wave have compressions and rarefaction. Compressions are really, compressions is synonymous with the crest, and the rarefaction synonymous with the troughs. And again, this is what the longitudinal wave look like. Compression, when the particles compress. This corresponds to the crest. Where the particles move apart, this rarefaction corresponds to the trough. And wavelength is from one compression to next compression. Okay. So when someone's speaking, you hear it. That's basically what's happening. The particles are moving back and forth from the source to your ears. Okay. All right. Now we come on to pressure. Um, you know, or as we say that, sound transmits energy, and you can relate energy to pressure. If you plot a plot of pressure versus time, going to give you a sine wave configuration, what you're accustomed to to seeing as a wave. Um, so if you plot um, your pressure against time, you get this sine pattern where you have crest, trough, crest, trough. So you can depict your longitudinal wave in a sine, in a sine pattern by plotting pressure against time. So even though sound is a longitudinal wave, it can be represented like this. All right, and we went over the frequency. Frequency is the number of complete cycles per second. 1 cycle per second is the hertz. We've been through that. We talk about the period. The period is a time. It's a time to complete 1 cycle. That's a period. Frequency is 1 over period, and period is 1 over frequency. We did that. Okay. We're not going to go into pitch and frequency too much, but people who do music have to know a little bit about ultrasound physics, um, so that they can understand what they're doing. Because pitch, have a certain definition. When someone say, "What is the pitch?" You have to know what they're talking about. Okay, so this is the frequency range of normal human hearing, and the frequency is 20 hertz to 20,000 hertz. That's the range of normal human hearing. So it is. So remember, 20,000 hertz is 20 kilohertz. So the range of the human hearer is capable of detecting sound wave with frequency 20 to 20,000 hertz. Okay, so you have to appreciate that. So when we talk about ultrasound, it is frequency above 20 kilohertz or above 20,000 hertz. And infrasound then is less than the lower range of frequency. So ultrasound more than the 20,000 hertz, infrasound less. Okay, and then pitch. If you were doing music, then this would be very important to know what's a pitch. The pitch is a sensation of a frequency. So high pitch corresponds to high frequency, and a low pitch corresponds to a low frequency. So when someone talks about pitch, it's actually a representation of the frequency. The sensation, high pitch and low pitch, have to do with high frequency and low frequency. We're not going to go too much into that, but when someone talk about an octave, it is actually if you have two sound waves that's with frequency that of say 2-to-1 ratio, and they interfere. So octave or fifth and what is just the interference of sound wave. So the octave is when frequencies one of a 2-to-1 ratio. So this frequency is twice as much as the top frequency. And when they interfere, you get a certain pattern. That's what they call an octave. And then a third is when you have frequency with a ratio of 5 to 4. So this frequency is 5 times and this frequency is 4 times. So the ratio is 5 to 4. And when they interfere, you get a third. These are musical terms. A fourth is when you have frequencies 3 to 4 and they interfere. A fifth frequency 3 to 2 and they interfere. So, music, if you're going to do music as a career, you have to do a little ultrasound physics too. So that is pitch. So pitch is just a sensation of the frequency. What about intensity? Intensity is a measure of the energy. Remember what we said, that energy is proportional to the amplitude. The exact thing is energy is directly proportional to the amplitude squared. So a low energy, the amplitude is lower. High energy, amplitude is higher. So when we talk about the intensity, it is the energy per unit time per area. Okay, so the intensity of the sound wave is the energy that is transported past a given area of a medium per unit time. Okay, so the intensity is a measure of the energy, but it for a particular time over a certain area. That is the intensity. Okay, so when you talk about the intensity of a sound, you're really talking about the energy, but it's for a specific time over a certain area. That is the intensity of the sound. And so if you want to define or to represent the intensity mathematically, you have to go through an exercise. First of all, you have to talk, what is the power? When we talk about the power of the sound, is the energy per unit time. So, and that's the definition for any power. If you want to see how powerful you are, you have to expend a certain amount of energy over a specific time. So the power is the energy divided by time. And then the intensity, it is the power divided by the area. Remember, the intensity is the energy per unit time over a certain area. So the intensity is the power divided by the area. And, the area over which the energy is being applied. So you can represent power, is the unit of power is watts, and area, of course, is meter squared. So the intensity is power divided by area, which is watts divided by meter squared. So, try and get that concept. So power, energy per unit time, and then the intensity is power over area. That's intensity. So you just have to go over it. So when we look at intensity, the intensity of sound wave decreases with increasing distance from the source. And as we said, the intensity is equal to the energy divided by unit time divided by the area. Energy divided by time is the power. Power divided by area is the intensity. So area, of course, the meter squared, so it's a distance squared. So remember, area is distance squared. So intensity is proportional to 1 over distance squared. So that is why the intensity decrease as the distance increase. So with increasing distance, the wave spreads out over a greater area, over a greater surface area. So if you just wanna just look at this, the top formula, intensity is equal to power divided by the area. If you are at a little distance away from the source of the sound, the sound is going to spread out over a larger area if it has to go a little distance. Or if you want to just simplify it, intensity is equal to 1 over distance squared, because area is distance squared. So the longer the distance, the smaller the intensity. Okay. We you know, when we measure intensity, we use the decibel. So I'm not going to go into that too much, but you know, when we measure intensity, we use the decibel scale. But the important things for you to remember is that the greater the distance, the lower the intensity. The smaller the distance, the greater the intensity. Just from what I've shown you before. Okay, so intensity is equal to energy per unit time per area. So the energy per unit time is the power, and A is the area. So the intensity is power divided by the area. When you talk about area, you always have to square the distance. So it's area is distance squared. So intensity is proportional to 1 over distance squared. The greater the distance, the lower the intensity. The smaller the distance, the greater the intensity. All right, so again, the decibel is a measure of the intensity. That's what we use. I'm not going to go into that too much. We already went over the speed of sound. You know, the speed of sound. You know the speed formula. The speed formula is speed is equal to lambda times f, which lambda is the wavelength and f is the frequency. So speed is equal to frequency times the wavelength. The speed of sound, because we're talking about sound, the speed of sound in a medium is fixed. It's not going to change. So if the frequency increase, the wavelength going to decrease, because the product have to be the same. Speed also is related to the inertial property, and we use the density to represent the inertial property. And it is so speed is inversely related to the inertial property, that's its density, and it is directly related to the elastic property. If you remember the formula, speed is equal to the square root of E divided by rho, which E is the elastic modulus and rho is the density. Okay, so you have, this appears in a lot of exams, so you have to understand speed is inversely related to the density and directly proportional to the elastic properties. So the elastic properties is the tendency of a material to maintain its shape and not deform when a force or stress is applied to it, elasticity. So it's a measure of the stiffness or rigidity of the material. The atom molecules, they have strong attraction for each other. And say elastic modulus, I elasticity, I elastic modulus. So for longitudinal sound wave is a longitudinal wave. So for longitudinal sound wave, the speed is going to be greatest in solids, followed by liquids, and then gases. Okay? Because the elasticity of the elasticity of solid is much greater than the elasticity of liquids and gases. Okay? That is why the speed of sound in bone is over 4,000 meters per second. Okay? It has a greater elasticity or elastic property. So the inertial property is just the material's tendency to be sluggish or changes in its state of motion, the density, the mass density of the material. So the greatest impact on the speed of sound, the density. So again, sound waves travel faster in a less dense media than a more dense media. Okay? So, so you have to draw everything. So if you remember when we draw the speed formula, okay? So you draw everything. If you can't draw it, that means you don't understand it. So it's equal to the square root of the elastic modulus, which is a measure of the elasticity, divided by the density. The greater the density, the slower the speed. The lower the density, greater the speed. If the elastic modulus or elasticity is increased, greater the speed. Solid more than liquid, more than gases. You have to understand that. Okay, so the speed, you can represent speed another way, where it's equal to the elastic property divided by the density. And if you vary the elastic property, you can impact speed in a specific way. If you vary the density, you can do the same. So you have to, because these things appear in exams, so you have to know. All right. Also, temperature, we went over that. So the speed is directly proportional to the temperature. Okay, speed is directly proportional to the temperature. But this is the one of the formulas that relate speed and temperature. Okay, the temperature affects the strength of particle interactions, and the velocity or the speed is equal to 331 plus 0.6 times the temperature in Celsius. So it's temperature in Celsius. Okay, so the greater the temperature, the greater the speed of sound in here, or the greater the speed of sound in any medium. So try and understand that. All right, so the speed of sound at 20 degrees Celsius is 343 meters per second in air. Okay, at standard temperature and pressure, the speed of sound in here is about 331. So the greater the temperature, the greater the speed. The speed of light in here is about 3 times 10 to the power 9 meters per second. Okay, and so we're not going to go through that. You can go through that. That's just if you become a meteorologist and you need to calculate time and distance from the storm and stuff, then you can go through that exercise. We went through that. We're not going to do the human here. You can go through that at your leisure. But interference, we went over the interference. Waves interfere. So the name is self-explanatory. When you interfere, you disturb, you combine. Okay, so it is the phenomenon that occurs when two waves meet while traveling in the same medium. So that is interference. And then constructive interference, where you have crest meet crest, trough meet trough, and then you get a resultant. And then destructive, where crest meet trough, and okay, we went over pressure. Pressure is energy per unit time. And then intensity is the pressure divided by area. Sound wave is a longitudinal wave. Okay, we went over your we went over standing waves and harmonic imaging. So again, people who, like, if you're going to do a degree in music, you have to know a little bit about ultrasound physics, because you're going to construct concert halls and you're going to have interference. You're going to have constructive and destructive interference. You don't want to construct your conference hall in such a way that some people not hearing anything, because you're going to have destructive interference throughout the hall. So you want to construct it. So yeah, you want constructive interference. So you might use certain material in the wall, some stuff in the ceiling, and so as to get more constructive interference so people can hear. Okay, so, and then we talk about noise reduction. We're not going into music. The thing about noise is sound wave. Remember when we talk about an octave, the fifth, the third, these are when you combine frequency with a fixed frequency. When you combine sound wave, fixed frequency, and you have a simple mathematical relationship between the frequencies. Noise is when you combine sound that has no simple mathematical relationship. The frequencies are very complex to when you add them up together, or when they interfere. So the mixture of sound wave with frequencies that have no clear mathematical relationship. That's the definition for noise. We're not going to go through beats, but as these are all music things. So if you were doing music, you'd know what a beat is. All right, so now we come to the attenuation of sound. So when you say something is attenuated, it's lessened. Attenuation is a reduction in intensity when sound travels through a medium. Remember what we said, that intensity is equal to the power divided by the area. And then when we simplify area is distance squared. So intensity is proportional to 1 over distance squared. So the longer the distance, the lower the intensity by just distance. So we know if the sound have to travel a longer distance, it's going to lose its intensity. You're going to have a reduction in intensity. Okay, so it decreases with distance, and it's due to the spreading out of the wave. But there are other things that result in attenuation, such as the absorption of the sound. That is the conversion of the sound energy to other forms of energy, such as heat. Okay, so not only that it's spread out and it's over a longer distance, there's a conversion of the sound energy to other forms of energy, such as heat. And then you have something called scattering. Okay, remember when the sound wave strikes a border, it's going to be reflected. So scattering is just a form of reflection. So reflection of sound wave in directions other than its original direction of propagation. That's what we call scattering. And there are different types of scattering. We have been through this before. Intensity. Intensity is the energy per unit time per area, which is really power divided by area. We've been through all of that. So there are different types of scattering. So remember, scattering is a form of reflection. Your sound wave is going to strike a border and it's going to be reflected. You can have what we call specular reflection, which is the one that you guys are more familiar with, which is a single incident wave giving rise to a single reflected wave, and it follows the law of reflection, as opposed to diffuse reflection, where the incident wave is reflected in many different angles. And this is when the surface is not smooth. You have an irregular surface, you have diffuse reflection. If you have a regular and a smooth surface, you have specular reflection. So this is your specular reflection, smooth surface, surface is irregular, you have incident wave and it's reflected in multiple different position, multiple different directions. Okay, we're gonna stop here, and so you need to go over